In 2021, Chase International launched their digital-only retail banking operation in the UK. Within a few years, they grew their customer base from tens of thousands to millions. In this session, we will show how their choice of AWS technologies enabled them to scale their operation while delivering a highly differentiated product to their customer base. My name's Altaf Hussain. I'm a Senior Analytics Solution Architect at AWS, and today I'll be joined by Bijan Fathi, who is the Head of Data Engineering at International Chase Bank. Let's get started. In our talk, we'll discuss how you can modernize your data lake by adopting open table formats, which allow you to scale your data analytics platform. Bijan will talk to you about how they used non-functional requirements to identify their scaling challenges and take remedial actions using AWS technologies. And finally, I'll conclude the talk by walking through a serverless reference architecture that helps you to build a data analytics platform in a cost-optimized and a scaling aspect. So, as successful businesses grow and acquire new customers, the challenge they usually face is to ensure that the underlying infrastructure can keep up with their demands. Traditionally, this infrastructure has always struggled with storage and compute. Traditional operational data stores, for example, you would need, if you wanted to accommodate or meet SLA requirements from a compute perspective, you needed to also increase storage, and therefore you ended up paying for redundant storage. Similarly, if your data volumes increased and you wanted to increase your storage, you ended up paying for unused compute. So the challenge here is how to scale your underlying infrastructure while at the same time keeping your costs down, ensuring that your cost does not increase at a similar magnitude. And this is why more and more customers are adopting a data lake approach to building a data analytics platform. A data lake is a central repository that allows you to store all types of data, structured, semi-structured, unstructured, and all types of data formats in terms of video, audio, text, and so forth. The advantages of having a data lake is that it allows you to store this data in massive quantities at a very cost-optimal way. And because all of that data can reside in one single place without being distributed across multiple data stores, you effectively get a single version of the truth. That holy grail that data analytics is always looking for. Similarly, a data lake allows you to store the data as is. And it gives you the flexibility to query that data and different types of data without having to impose a schema beforehand. This is the concept of schema on read as opposed to schema on write. You might be familiar with these terms. And very importantly, because it's able to store all that data in one place, and it is a storage layer, you are effectively decoupling your storage from your compute. So you don't have to pay for extra compute resource just to manage your data increase volumes. And what that means is that you're able to bring your query engines of choice to the data lake. So you can query the data with Athena or Spark or any other tool that you want to use. And finally, the data lake allows you to retain your data for a very long time, as long as you like. What this means is that you're able to analyze historical data, gain additional data insights, perform replays on your data in order to identify root causes or additional analytics. A data lake consists of a storage layer. This is typically a distributed file storage system like S3 or HDFS. This storage system allows you to store different file formats such as CSV, JSON, Parquet, Avro, ORC. And this storage system allows you, like I mentioned, to bring a query engine to the data lake. So you can use Spark, Flink, Trino, Athena, or Redshift to query the data in your S3 data lake, for example. How you query that data is via the metadata. The metadata layer is simply a pointer to the file location. And your query engine will use the metadata to access that file and read the records from the file. But how should we structure the file system? So how should we structure the files in our data lake so that we can query that data in a performant manner, in an optimal way? Now, if you're familiar with data lakes or you've built a data lake, you would have come across the concept of a Hive table format. A Hive table format basically allows you to structure the data in your data lake as a table. It uses directory listings, which are effectively partition fields, to structure the data in your data lake. And by doing this, it's able to prune the partitions at runtime, thereby reducing the amount of data that needs to be scanned, effectively improving your query plan and your performance. Okay? The good thing about this is obviously it avoids doing full table scans. And the Hive table format also supports multiple file formats, such as Parquet, ORC, and Avro. However, it does have certain disadvantages or limitations. Because the Hive metastore is essentially a pointer or a database of pointers to the directory listings, there is that overhead in terms of maintaining the listings and ensuring that everything is in sync with the file location and the data in the file location. Also, it doesn't support row-level operations. So there is no support for updates and inserts. And if you want to do this, there's workarounds, but it's very inefficient. And finally, it doesn't support multiple concurrent writes and reads on your file system. And also, a final point, because the partitions that are used to structure the data on your data lake are explicit or have to be made explicit before the data is loaded, the end users need to be aware of the partition schema in order to basically utilize them effectively. Now, it's because of the limitation of Hive table format that open table formats such as Apache Hudi, Apache Iceberg, and Delta Lake were introduced. These build abstractions on top of the file formats, and these abstractions give you certain key benefits that address the limitations of Hive tables. The particular features that they give you are database features, like row-level operations, which allow you to basically perform deletes, inserts, and updates at a record level within the data file, and therefore ensuring that your transactions are ACID compliant. They also recognize the fact that as your data evolves, there is a need to basically manage evolution of your schema. This is basically adding and removing columns. This is supported by these open table formats. And of course, they track changes in your data lake. And these changes are really important because they allow you to do version rollbacks. They allow you to basically time travel, because what happens every time changes are committed to the data lake, a snapshot is taken. Those snapshots are preserved, so you're able to then basically query a particular snapshot as a point in time view of your data. And of course, these data lakes are designed to be highly performant, therefore they manage concurrent writes and reads, which is vitally important for any data analytics platform, because typically if you have petabytes of data, that data is going to be written by multiple producers and it's going to be sourced from multiple data sources. You do not want to be in a situation where you're writing data into a data lake one after the other in a sequential way. That's not optimal. And similarly, if you make that data lake available to multiple users who are coming in there with Spark or Athena or Trino and want to query that data, they should be able to query that data without any contention. At AWS, we support all of the open table formats. And we're seeing increasing customer adoption for these formats for building a modern data analytics platform. Apache Iceberg is proving particularly popular. And it's not difficult to see why. Because Apache Iceberg allows you to treat your table in your data lake as a SQL table. It brings the reliability and operational features of a traditional SQL table. And at the same time, it allows you to query that data and write to that data through multiple different data concurrent writes and reads. How it does this, if we go back to looking at the comparison between Hive tables and an open table format, like Apache Spark, the way it does this is by simply inserting a metadata layer between the catalog and the data files. If we dig a little bit deeper into the architecture of an Iceberg table format, we see that at the top we have the Iceberg catalog, which is basically a metadata pointer for your Iceberg table. So when you execute a SQL operation, this is a read operation, but it could be a write operation. If you execute a SQL operation, the Iceberg catalog will identify the current metadata file. That metadata file tracks changes. It has pointers to the snapshots, the various different versions of the table content. It basically has information on partitioning, on custom properties, and it's able to identify the current snapshot that you require. The current snapshot itself will then basically map to or point to the manifest list, which will be a list of manifest files. And these manifest files, we can prune them using the partition range. The partition range pruning will then basically identify the relevant data files, which in turn can be partitioned can be pruned by the partition field and the column statistics. What this architecture basically demonstrates is that Iceberg is able to perform at scale with petabytes of data by using advanced filtering techniques such as column statistics and partition pruning. And because it tracks changes to your data lake, you can perform version rollbacks. You can do point-in-time analysis of your data. So when should you consider using Apache Iceberg for building your transactional data lake? Well, like I said, Apache Iceberg, created by Netflix, was specifically designed to handle huge amounts of data. If you want to treat the data in your data lake as a single table, Apache Iceberg is your best choice. And because it uses SQL, it gives you all of those SQL operations that you're comfortable with using and supports them in a database-like way. So gives you atomic changes, but gives you ACID compliance, all the kind of reliable behavior that you would expect from an operational data store that uses SQL. And this is a key feature, and actually a really good feature of Iceberg: hidden partitions. Typically, your data volumes will change. They'll increase, hopefully. And as they increase, the query patterns will change. Now, in a traditional data lake using Hive tables, managing the evolution of query patterns was a painful process and a very, a significant overhead. With Iceberg, you don't need to do that. As your query patterns change, Iceberg at the back end will update the petition field to reflect changes to your query patterns. So for example, if you start, say you start initially querying data in your data lake, which is only in the terabytes by filtering on month. But as your data volumes increase to petabytes, you realize that you can't filter by month anymore. You have to filter by a much more finer, granular field like date. Iceberg will detect that, and it will update your petitions to reflect date as a new petition field. It will still keep the old petitions. So if you're querying old data, new data, it will basically use an advanced feature called split planning to manage those different petitions. And it's this kind of optimizations that Iceberg has that really makes it a very popular choice for transactional data lakes. We've already mentioned advanced filtering. It has all of these: petition pruning, petition range pruning, column statistics. It heavily leverages these features in order to give you performance at scale. And as I said, it tracks changes, and it ensures that those changes are atomic, so that if you are reading from a snapshot, you are never reading partial or uncommitted data. If a producer is writing data into that table, you won't see those changes until they're committed. And once they're committed, that will be a new snapshot. And the next time you execute a read operation against that table, you will point you to the new current snapshot with the new data. And of course, we've mentioned this, it supports multiple concurrent writes and reads, and it supports multiple writes through optimistic concurrency. Optimistic concurrency is, put simply, the idea that if there's multiple writes being executed against a table, as long as those writes are compatible, they will succeed. There's the optimism. So there you have it. So now I'm going to hand over to my colleague Bijan, who will talk about how Chase used transactional data lakes and AWS services to build their platform. Thanks, Bijan.
Thank you. Thank you. Hello, my name is Bijan, and I'm leading data engineering at ICB Chase UK. Our story, we started cloud first, AWS first, and from 2021 until now, more than 2 million customers, 16 billion reposits, and more than 1 million daily transactions. That led to a rapid growth of our data and all the data use cases. Initially, we had a very humble setup of a data platform, which was just sized for 100,000 customers. And then we discovered that we have to scale it within a certain time, up to 20x, but still supporting it. In our large bank, we have a very strict controls environment. So therefore, our initial setup was Kubernetes hosted with the components that we are allowed to use. The microservices were producing Avro on Kafka, so we were landing Avro files. We had our internal Spark setup for processing and also for feeds, and the query layer was a Presto setup. Visualizations was pointing to Presto, and we had only a few 10s to 20 users using these setups. This was working fine for 100,000 customers. But as we grew very quickly, we had to build in parallel a setup that was scaling with the needs that we had. So we had to reconsider the choices and scale up. For the 20x increase, we choose the technology from the stack that we have discussed before. Glue catalog for our repository. We used a serverless Athena query engine to enable scale and reducing a lot of issues we see with noisy neighbors and others of shared infrastructure. We chose Iceberg to reduce the time to query of data. So when we were landing data in small files in Hive. There is a time that we need to rebuild it to have it efficient. That could take between 2 to 4 hours depending on scale and capacity. With Iceberg and the way of streaming landing, we reduced it to minutes. We moved from Avro to Parquet, which reduced massively our shuffle volumes. So we were talking about 90 petabytes of shuffle per month. That significantly reduced. How did we redesign the setup? So initially, our ingestion setup, we are using AWS Glue streaming as a serverless streaming platform to land incrementally in small increments on the S3 in Iceberg. The incoming flows. Therefore, we have a few. So we have batch data and streaming data. The streaming data on the top left is produced on Kubernetes, lands on Kafka, and the streaming jobs of Glue are reading it and writing it in very small increments to Iceberg. And all new streams are discovered and registered in the Glue catalog. As we have an internal setup of Kafka with a custom authorization, we need to work with the authorization systems to do the discovery and the setup. We have also the requirements that the producers of the data need to grant the data lake access to actually land the data, and therefore we have a separate discovery and landing process which automates the whole process. And we moved from manual onboarding of the data and individual Kafka Connect setups to a fully automated data landing at scale. The processing layer, that changed to, we are using Athena for internal processing and have also enabled an incrementalization of the layers of the processing, as well as enabled the users to use dbt as a more convenient software to manage their transformations. The transformations are all registered as views in Glue catalog, and therefore we can also discover and version control them over that. And some of the data sets are even pushed after that directly into DynamoDB. This setup with the ingestion uplift and the transformations with serverless compute with significantly more scale enabled us also to use near real-time cases, which with the previous setup was not possible due to multiple hours of visibility of the data. The analytics layer, as we have strictly separated the processing layer from the analytics layer, we could also isolate noisy neighbors at one side. On the other side, guarantee better latencies to the consumers, and also isolate dedicated compute for read performance to individual groups of users, as our consumer base grew from 20 to more than 150 users and multiple use cases. We have opted to a push model, as our internal controls require that all operations on S3 are actually audit logged. So therefore, read operations on a lake with 1 billion files would also produce quite a audit log bill. So with Redshift, that simplified that. In addition to that, we have a strict policy who is allowed to see what at what times. So therefore, we are using dynamic data masking in Redshift to enable that with a separation of the view layers. Putting all together, we get our effective reference architecture of our data platform, which is enabling us to perform more than 20x scale and is in nature serverless and enables us to scale at optimal cost. In numbers, what have we solved? We have more than 3,000 analytical views for analyzing the 2 million plus customer behavior, and more than 120 terabytes of transformations every day. The overall aggregate processing time that Athena runs for us is more than 400 hours every day, in only a few hours, obviously. What are our key takeaways? So we focused on the right metrics. So we focused on our NFRs, organizing our setup to fulfill and adapting it to uplift our stack. We removed operational overhead as we moved from a lot of self-managed setups that are complex at scale and in SLAs to scale. We moved to a serverless setup, which we are a bit more hands-off, and we are utilizing AWS functionality to isolate workloads and enable different scaling groups. We built the whole platform in parallel to the existing platform, as well as double-landed the data. So we made the transition as safe as possible and gradually moved use cases, so therefore we could build it up as we were using it and enabled it without any interruption and without any setup. So we made small incremental change. And by using Iceberg, by using Athena, by using Redshift for the individual use cases, we think we have used the right tools for the right technologies and continuously evaluate that for use cases. Overall, the platform had hours of delay between data landing and being able to query and very limited query capabilities, but with the serverless setup, with the right tools, we enabled near real-time and even some real-time use cases in that setup. And most importantly, keep it simple. Even though some of these technologies are quite complex, the overall pattern is very simple, and we reduced, isolated the use cases, reduced the patterns to the best and simple setup that we have. And that enabled us also to deliver that in reasonable time while we are maintaining the other platform. For the next, I hand back to Altaf.
Thanks, Bijan. So you've heard from Bijan on how Chase UK's data journey and how they re-architected their platform to address challenges with scale. I'd like to conclude the talk by walking you through a reference architecture showing how you can rapidly build data lakes as well as data pipelines using AWS serverless technologies as the building blocks. The choice of going serverless is quite simple. We are seeing more and more customers moving to serverless for the simple reason that it's making their lives a lot easier. It makes their job easier. With AWS serverless technologies, you get well-architected fundamentals built into the services by AWS. So you can concentrate on basically producing differentiated products. You no longer have to worry about scaling the service because that will be done by us automatically with demand. You can leverage the reliability and security that's built into the services. And of course, with a pay-as-you-go model, you can manage your service in such a way that you can reduce cost. And it goes without saying that is easy to use. At AWS, we offer more serverless options for data analytics in the cloud than any other cloud provider. Depending on your particular use case, you have a range of different services to choose from. So if you want ad hoc querying, you can use Amazon Athena. If you want to manage your data governance at scale and set permissions using database-like features like granting and revoking, or you want to do permissions through tag-based access control, you can do that with AWS Lake Formation. For big data processing, we have Amazon EMR and AWS Glue. AWS Glue is a managed Apache Spark environment that allows you to process huge amounts of data. It comes with a Glue Visual Studio, which allows you to drag and drop components of ETL so that you can build complex data pipelines without or while minimizing the amount of coding that is required. With Amazon EMR, you have access to the open source Hadoop framework and all the applications therein, like Spark, Hive, Presto, and so forth. If you have streaming requirements, you have a choice between Amazon MSK Serverless and Amazon Kinesis. Now, which one you go for will really depend on your particular use case. For example, if you have very high throughput and you kind of need to retain that data for a very long time for regulatory purposes, and you want to enforce exactly one semantics, then MSK Serverless would be the right choice for you. If you have, let's say, less stringent requirements, you have a consumption layer that can basically manage the deduplication of records, for example, then you can opt for for Amazon Kinesis. But this is really up to you. We, or myself, in my role, are here to kind of guide you to the best choice depending on your particular use case. Moving on, if you have data warehousing requirements, we have Amazon Redshift Serverless, which is a cloud-native distributed data warehouse designed to kind of crunch and aggregate petabytes of data. And finally, for BI purposes, we have Amazon QuickSight, which is our cloud-native BI tool with built-in natural language querying capabilities so that you can build interactive dashboards. So let's have a look at the component-orientated serverless analytics platform that we're proposing for you in our reference architecture. At the ingestion layer, we saw how Chase were using AWS Glue to do both batch and streaming. And that is a perfectly good option. If you want to do micro batch processing, Glue can do that for you, and it gives you near real-time streaming capabilities. However, again, depending on your particular requirements, you might have the need for real-time streaming and might need to process and retain that data for longer periods. In that case, you can use Amazon MSK Serverless. It will allow you to scale your resources as the demand and throughput increases. So you don't have to worry about right-sizing your Kafka cluster. You don't have to worry about over-provisioning your cluster. And because it uses a throughput-based pricing model, you only pay for the volumes that are streamed and retained. And of course, you can use MSK Connect, which basically allows you to deploy, scale, and monitor your connectors and the data coming in and out of your MSK cluster. On the batch side, you can use AWS Data Migration Service Serverless to basically migrate your data from operational data stores. AWS DMS Serverless also allows you to change data capture by basically analyzing the logs on your operational data store. And it does this without any contention to those operational data stores. On the processing side, you again have a number of options. Chase used Athena to run thousands of SQL queries. They orchestrated it with dbt, which again makes perfect sense in certain scenarios. However, if you want to do additional data processing, more complex, build complex data pipelines, you can choose Amazon EMR Serverless with its open source, easy to use Apache Spark environment. And also it gives you Apache Hive as well. You can also use AWS Glue, which is, again, managed Apache Spark with Glue Visual Studio to build complex data pipelines. So there's a lot of choices. It really depends on your particular requirements, functional and business, which one you go for. On the consumption layer, we can consume the data from our transactional data lake using Athena for ad hoc querying. We can consume the data through Amazon Redshift Serverless for analytics, data warehouse requirements. Redshift supports Iceberg format, so you can query Iceberg tables. And it also has a built-in Redshift query editor, so you can use that to write and build your queries. And of course, you can use Amazon QuickSight on top of Amazon Athena or Amazon Redshift to build your interactive BI dashboards. So putting all of these together, you can see that we have a reference architecture that will support most, if not all, your workloads. And the choice of serverless technologies will really depend on your particular SLAs and the varying levels of technical proficiency of your users. So in terms of recommendations going forward, 2 things to take away from this talk. One is, if you're building a data analytics platform, please consider using open table formats. Open table formats address many of the shortcomings of a traditional data lake. And the adoption of open table formats will allow you to not only achieve the single version of the truth that you're looking for, but also support multiple writes and multiple use cases. And secondly, consider going serverless. It removes the overhead of managing the underlying infrastructure while benefiting from the built-in, well-architected reliability and security that comes from AWS services. And with that, I'd like to conclude this session. On behalf of myself and Bijan, I'd like to thank you for attending our talk. I hope you found it really helpful. We will be here for further questions if you have any. Please, before you dash off, take a minute or so to complete the session survey. Your input is really important, so please, help us sort of to improve our, our talks going forward. Thank you very much. Enjoy the rest of the summit.